are urban areas where most popularity of the Earth lives. And in these parts of the world, natural surfaces are converted into surfaces of artificial materials, which have specific heat characteristics. So these parts are exposed to additional heating. And along with this, also, these places are very vulnerable to climate change. And we choose the city of Dubrovnik. And the third reason are extremes, which we all know that with climate changes, we will have increase of weather extremes such as heat waves, floods, severe storms, etc. To study urban heat law of the city of Dubrovnik, we needed some data like temperature, relative humidity, and wind. And we were applying an urban climate model named Muklimo3, which is developed in a German meteorological service. And for that model, we applied measured data, which were collected at the meteorological station in Dubrovnik, and also regional climate models data from Eurocordex initiative. And in this table, we can see 4 combinations of data which were used to study future climate conditions. Here is also, you can see our domain, which had a resolution 100 kilometers. And here also you can see land use, land cover classes, which were used to explain how our domain is seen from the model. So in this study, urban heat load was quantified in the terms of climate indices. We used hot days and tropical nights. As I already said, for urban climate modeling, we were using Muklimo3. And we did simulations which included different modifications of land use, land cover. So we had a control simulation where we didn't change anything. Then we had a modification which we called ABVI, where we set albedo of the roofs to 0.5. We decreased fraction of built up for 10%. And we increased fraction of low vegetation for 20% and decreased fraction of impervious surfaces for 20%. Modification AVI is the same, but here we didn't have modifications of fraction of built up. And in modification A, we only changed albedo of the roofs. So we had 3 experiments. First was to simulate referent climate conditions, for which we used measured data in the period from 1981 to 2010. Then we had hypothetical extreme climate conditions, where we choose 10 warmest year from the 1961 to 2021, and this was also based on measured data. Here is the table with the years which we used. And as you can see, only 1919 fourth year was not from 21st century. And the third experiment was for future climate conditions, where we used RCM data, and that was RCP 4.5 scenario. And here we calculated mean summer temperatures for those experiments. And we find out that according to these results, we see that something that is now recognized as extreme in the future could be possibly expected to be some average state. So results. Firstly, we calculated average numbers of climate indices in those experiments. First row are results for hot days and second for tropical nights. And here at the first we see that the urbanized parts of the city, which are here and here, are, as we expected, warmer than rural areas. And the coldest areas are, of course, forests. But it is evident that in extreme and future experiments, this urban heat load will increase. Here we show a distribution according to Lulz classes. And you can see that the greatest heat load is obtained for residential area and for public area. And that remains same in all experiments for both indices. However, if we take a look, for example, on Lulz classes which belong to green area, we can see that class 21 is warmer than, for example, 28, which represent forests, and for example, 29, which represent bushes. And 21 belongs to the parks, which are mostly stated in the urbanized parts. So they are surrounded with the buildings, and that's why they are warmer than some originally natural places. We can also see that during the night, we had a decrease of urban heat load because these classes represent a decrease of fraction of built up. And here we wanted to somehow describe urban heat island intensity, but we faced one challenge because in Mediterranean cities, they are mostly squeezed between sea and mountains. So it's not that easy to find what is here a rural area. So we decided to calculate differences between class 2, which is highly built up, and calculate differences to class 21, which represent parks. And the other difference is for class 29, which represent vegetation associations. We calculated those differences for the entire domain, D1. And here we see that those differences are bigger for class 29. While for parks, we can see that in those experiments, these differences are getting smaller as the climate is becoming warmer. But here is also important to say that there are much less classes which represent much less cells which represent parks. So we then decided to take a look at some more compact areas. So then we decided to calculate differences for this domain D2. And here we had a lot of cells which represent forests. So we can say that is high urban vegetation, while this part represent class 29, and we can say that this is low urban vegetation. So we again calculate the differences for class 2 and classes 28 and 29. And we find out that during the day, there is bigger difference between high urban vegetation. However, these differences are also decreasing in warmer climates, while for low vegetations, these differences are smaller, especially at the day. And as we all know that the climate warming is continuing, we wanted to see, is it possible to somehow reduce this urban heat load? So we applied those modifications in land use land cover, and to see how big effect of reduction we can get. So again, the first row is our results for hot days and the second for tropical nights. And the results show that if we apply those modifications, so ABI, ABVI, we see that we get some reduction of urban heat low, but this reduction is mostly obtained for those areas where we applied changes. So according to these model results, we cannot expect that this mitigation will spread all over the city. And the results are similar for all three experiments. If we take a look at those classes where modifications were applied, we can see that, for example, for classes 1 and 2, which have the highest fraction of built up during the day, so for hot days, the most efficient measure is measure where we change albedo of the roofs. And that is obtained also for extreme and future climate conditions. While for the all other classes, the most efficient is showed for ABVI, where we change albedo, fraction of built up, fraction of low vegetation, and fraction of impervious surfaces. And we can explain that due to fact that in classes 1 and 2, we have a lot of buildings. So there are a lot of shadowing effects. And during the day, that's why the albedo of the roofs is the most efficient. But if we take a look at the results for tropical nights, we see that for all classes, the most efficient is ABVI modification, which included reduction of fraction of built up. So we have more spaces between buildings, and here ventilation processes could be better than in the case where we have a lot of densely built up buildings. And to conclude with our results, we find out that the future climate means summer temperatures are expected to be close to the current extreme summer temperatures. Also in warmer climate conditions, high urban vegetations show that it loses its cooling efficiency. And we also find out that the modifications in land use, land cover show some weak impact on urban heat low mitigation. However, this impact is not good enough to reverse warming caused by global climate changes. Thank you.
Thank you, Mariana, for a nice talk. And we have some time for questions. Anybody? So then I can put my question. So according to your experience, would it be efficient to increase vegetation in cities?
Well, that's a really complicated question because high vegetation has its pros and cons. And one of the cons is that during the night, it can block radiation cooling. So I think we should do more research about how to implement it to have some good results in reality.
Okay, thank you. If there is no other question, so the next talk is going to be given by Lydia Sernets. How the risk of heat waves will change in the future decades in Croatian cities.
Good morning, everyone. Thank you for coming. The reason why this is the topic is climate change and its influence on health. So you can see in the inner circle that because of increase of CO2 level, there will be rising of temperature. And therefore some other things will happen. So with the rising of temperature, we will have more extreme heat that will influence heat, mortality, illness. Also, extreme heat will cause severe weather like we had this summer, 19 July, you all remember. So we also have some death, unfortunately, some dead people. Also, air pollution is a big, huge stuff that influence our health. Change in vector diseases, new species in our area also influence as well as ecology, but also the health, human health. And there is a huge problem of allergy. It's well spread all over the world. Each year there are more people that are suffering from allergies. The quality of water and also the resources for water are something that is under question in the future. And of course, at the end, what is really connected with the topic of this conference is the food, quality and security and production of food. So I will concentrate here on heat and health. But as you probably all know, all those consequences caused by climate change are not spread equally over the world. And the last days, I found the data that only 23% Ministry of Health are using climate data. Therefore, there is initiative, joint effort between WMO and WHO to look those topics as a common problem. This year was published the article that was very well, media was very interested in this. More than 850 cities all over the Europe were analyzed regarding the heat waves, not just heat waves, but also cold waves, so extreme temperatures and mortality. Croatia was also included, but what was interesting here, the data from Croatia were not the same as in some other cities. Of course, Croatia was not the only one country that was included in this study the same way. So there are countries that have the good database, and those data are in multi-country, multi-city database. But Croatia was analyzed by 7 cities and by approximation data. So what was the result? Result of this huge study was that cold waves caused more deaths in global than heat waves. And of course, elderly people are more influenced than younger. But the very interesting for media was also that Croatia has the biggest number of deaths regarding the heat waves. I suppose the reason for that was because there were not real data included in these countries. So I think we have to take it with a pinch of salt. Yeah. And now the last year IPCC climate change report issued that heat is growing health risk, that climate change is significantly increasing exposure to heat waves, that certain groups face more risk regarding heat, and that also urban heat islands affects more severe danger to some people in the cities. One of measure of adaptation is heat action plans. We have it well developed in Croatia, so we are doing it for more than 10 years. The Ministry of Health is organizing this action, and Croatian Med Service is very actively included because we are issuing the alarm. The base for this system was developed according to mortality and meteorological data, long time series for minimum and maximum daily temperatures, and for 8 different parts of Croatia, We have defined thresholds, fixed thresholds for moderate height and very high risk. So according to those criteria, this is 21 years how the issued alarm system could be. So in yellow, there is a moderate, in orange, high, and very high in red. So you can see that in 2000, the number of issued alarms is smaller than how we approach the up of the panel. So of course, each year has different number, and the alarm is not spread unique during the time. Here we are representing the summer period between 1st July to 31st August. The 2022 is the same. I mean, just in first row is June, July, and August. So you can see how was last summer in 2022. And here is presented from 1991 to 2022 period, the whole number of issued alarms for the whole Croatia. So we just sum up for all 8 areas, and we can see that this number is really differing from year to year. But what you can also notice that 2003, very hot year, was also here presented as the year with the big number of alarm, but the highest was 2012 in Croatia. Also, the last 2 years are among the highest number of the biggest number of issued alarm. And now what is actually the topic of my talk, I will just briefly present you what we wanted to see, how it will change in the future. So we use daily maximum and minimum temperature for one ensemble of models. We used it for moderate and pessimistic scenario. Yes, we have 3 RECCM force with 3 GCMs, and we apply the same criteria as we do in reality. We spread the future into 3 periods. There are cover 30 years period, and we compare it to, let's say, P0 period that is between 1991 to 2020. We covered summer season, and results are presented as ensemble of all 9 members together. So what I'm presenting here in the left column are 3 the same graphs. This is observed change in years from 1991 to 2020, as you already saw, but I put it 3 times. Yaron, can you help me? I'm sorry. Okay, on the right side, there is a matrix of 3 RECCM forced by 3 GCM. In a rows, there are GCM. In a column, there are RCMs. So the third column is the RECCM simulation that is produced in the HMZ. As you can see, figures are differ, and that's normal. But what you can also see that in the left column, we have more red alarm than we have in simulated present climate. This is something that we have to take into account, and this is something that we have deal it in the future also. What we did next, we also did projections for, as I mentioned already, 3 time spans in the future. Here I'm showing just P3, that is 2041 to 2070 on the right side versus P0. You can see that in the middle of the century, we will have really much more alarms. To summarize it, here are the numbers. I will not go now through this table, but here we are showing in the first left column the modeled present period. Then we have P1, P2, and P3, and we are showing it here for each city, for 8 cities: Osijek, Zagreb, Karlovac, Gospić, Knin, Rijeka, Split, and Dubrovnik. And then in the right side of the table, we are showing the differences. If we sum all numbers of issued alarms, again, just to compare a real situation in P0 and modeled, we can see that models in ensemble produce less alarms than it is in reality. But if we look in the future from 2021 to 2070, we can see very obviously, especially for pessimistic scenario, that the numbers of alarm is really increasing. So to summarize, we got some results. The total number of observed days during which there is a risk of heat wave affects the human health within 1 year, very specially and temporary. Of course, there is not the same number in the inland of the country as in the northern part of Adriatic or in the southern. It also varies if we sum it all over the Croatia. And we got an increase in the total number of warnings by 2.5 warnings per year for the whole Croatia in P0 period. The lowest number, as you already saw, was in 1997, just 3 warnings, but the highest in 2012 and then in 2003. And the model ensemble mostly underestimate the real warnings. What we can expect in the future, for a moderate scenario, we have an increase of warnings for 1.2 per year by the end of 2070, and almost doubled for a pessimistic scenario. Numbers of all warnings increase from present time towards the future, with the most pronounced increase in P3. And the last one, the change in the number of warnings by risk category, shows that by the end of the century, the number of very high risk will increase the most, and especially at the east of Croatia for the pessimistic scenario. What is our next step? We notice already that models has a bias. Mostly for XCM was warm bias, but we have to look in some other also RCM that we use here. So we would like to see how bias corrected input data will change our results. Thank you for your attention.
Thank you, Lydia. Obviously, it will be hot in Croatian cities in future. So some questions? No? Nobody? Okay, then we can continue with the next talk, which is Ivan Lončar-Petrinjak about drought monitoring in Croatia, current status and perspectives.
Good morning, everyone. My name is Ivan Lončar-Petrinjak. I work at the Croatian Hydrometeorological Service. And today I will be showing you the joint work of my colleagues and I on the subject of drought monitoring in Croatia. So drought first. Drought is a natural phenomenon, as we all know, that involves a shortage of water supply. This water supply is primarily and usually caused by a lack of precipitation. This drought can have serious effects on flora and fauna, inland waterborne traffic, and also in the inland waterport traffic and economy, of course. As such, can cause natural devastation and economical losses. But drought drought can also be amplified by other factors, not just lack of precipitation. These factors include the higher air temperatures, existence of air circulation, which increases evaporation, and low air humidity. This is an example of a drought monitoring product used in Croatia, the standardized precipitation index. This index uses only precipitation, or rather the lack of precipitation, as a variable. It is used on several time scales. But with rising air temperatures, which are sure to rise, there is a change in circumstances, and these new circumstances call for a use of a new index, perhaps one index that is dependent on this air temperature. So in this study, we use the standardized precipitation evapotranspiration index, the SPE, which uses water balance and not just precipitation. Water balance is the difference between precipitation and potential evapotranspiration, and this temperature effect is captured within this potential evapotranspiration variable. But to successfully use it and apply it, we first need to test which statistical distribution would best describe this new water balance variable across all of Croatia's diverse rainfall regions, precipitation regions. So in this study, we took our goals as to investigate to find which distribution would be best fitting for the water balance variable. Then with this distribution to calculate the SPEI and compare it to SPI. And lastly, to investigate, to describe what changes will happen between two climatological periods in drought characteristics. So the data we used were from 31 main meteorological stations in DHMZ monitoring network. Data included monthly precipitation and monthly averages of daily minimum and maximum temperatures. Data spans from 1961 to 2022. And for the calculation of potential evapotranspiration, we use the Hargreaves-Samani formula, a modified version, which is shown here. Stations are grouped in 7 regions, and these regions go from 1 to 7, from easternmost region counterclockwise to southernmost Adriatic region. So to find the distributions, we considered five of them. They're listed up there, and to find the parameters of the distributions, we used the method of L moments. We found L moments, then the parameters. These L moments were then graphed on L moment ratio diagrams for first look on our first results. But further, then we performed Kolmogorov-Smirnov tests on this data within the Monte Carlo simulations. After that, we found which distribution would fit the water balance data best, calculated the SPEI, and compared it to SPI. After that, it was a visual comparison. And then again, a visual comparison between the two periods, comparison of drought parameters, including duration, occurrence, and intensity. So these graphs show the moment ratio diagrams of the empirical data and fitted distributions. The dots represent empirical data, L moment ratios of empirical data. The colors of each dot, one dot is 1 month in a year of one station. Color of dot represents the region this station belongs to, and the colored lines represent theoretical L moment ratios of the 5 distributions. Now, the ideal case here would be if these dots would lie closely to one of the distributions, for example, this blue line here. But this is obviously not the case. But that would mean that this particular distribution describes the data best. But this is not the case, and instead we see that perhaps the lowermost distribution, which is the Pareto, generalized Pareto distribution, would not describe the data properly. But we still included it in the Kolmogorov-Smirnov tests. So these tables show the successful cases of Kolmogorov-Smirnov tests, Kolmogorov-Smirnov goodness of fit tests. The upper table shows the percentage of cases in which a particular distribution described the data good. Percentage of cases where the test was successful. We see that the generalized logistic distribution fits the data best in most cases. On the lower table, a similar result is shown, though here we have a grouping by month and time scale, and distribution which fit the data best in that case was shown. In most cases, we see again that the generalized logistic distribution was a best fit. Therefore, we used it for the calculation of the SPI. Here, we see time series of the two indices, the SPI and SPEI, overlaid. Shaded gray areas are SPI and black line is the SPEI. We see an overall good agreement between the two indices in both sign and intensity. But looking closer at only summer months, we see that SPEI, which is the right column, shows a worse drought in summers when it was hot, extremely hot or very hot. In some such cases, even the SPEI assigned the drought severity index to a stronger category. In such cases, being 2003, 2012, and 2017. Next, these graphs show differences between the two indices in 4 seasons. It's important to describe what the colors are. The blue color is a positive difference between the SPI and the SPEI. This means that the SPEI shows the more dry conditions or less wet conditions. We see an obvious trend in the 3 of the 4 seasons, a rising trend. We could describe this as a temperature effect which SPI, EI can see and the SPI cannot. For a spatial comparison, we have SPI on the left and the SPEI on the right for the case of a summer drought of 2022. Immediately we see that the SPEI shows more area covered by drought, which can be seen also in numbers here in the little histogram. But this more area covered by drought is in correlation with the fact that this summer was extremely hot, indicated by the picture above, which shows temperature anomalies for this season. So these graphs show this in particular is a mean dry spell duration graph on several time scales. Mean dry spell durations per region, region 1 to 7 here, from easternmost to southernmost, the Adriatic, compared between 2 climatological periods, and timescales are up here. First, you can see that on the lower time scales, the mean dry spell durations overall increase in the second period. But on larger time scales, there is a specific spatial redistribution in these graphs, but generally also the duration increases in the second period. In some of the regions, but in regions such as these, it falls. In continental regions and in continental and the southernmost Adriatic regions, it falls. The mean number of dry spell events seems to hold its number in the second period or increase it, which is more evident in the second period on larger timescales and in regions 3 and 4, which are mountainous hinterland and mountainous regions. The mean number of extreme events is mostly higher in the second period, most noticeably in regions 1, 2, and 3, which are continental and mountainous hinterland. There's a specific case of region 5 where it severely drops, but that is perhaps a case for itself that should be investigated. So to conclude, in this analysis, we found that the generalized logistic distribution was the best fit for most of the cases, for most of the analyzed cases. There was a general agreement between the two indices in both sign and intensity, but looking closer at their little differences, we found that the SPEI index, that depends on temperature, shows a greater drought in times where there was higher temperature due to surface water evaporation or evapotranspiration when including plants. There is a Also, by this index difference, we suggest that this might be the ability of SPI to detect drought earlier than the SPI. In the recent period, there was a noted tendency toward longer dry spells on smaller time scales, but the opposite was true for larger ones. And general increase in frequency of extreme events was also noted, except in some specific cases. This increased severity of drought events can be attributed to rising air temperatures globally, which consequently draw more moisture from the surface, increasing drought effects. And now that we have found which distribution fits the data best and are ready to use the SPI ready to use SPI in Croatia's ODM, drought monitoring systems. The next step would be to find to develop a platform that would further analyze drought and possibly forecast it. By this means, an interregional Central Europe project link forecast was started this year, and here is the link. So if anyone would be interested, they can check it out for themselves. That would be it. Thank you.
Thank you, Ivan, for your nice talk. Obviously, temperature does matter
Yes.
in Croatia. Yeah, so in future, even will be worse with drought, I suppose. So, some question from the audience? Okay, if there is no, we will keep the time and continue with the next presentation, which will be online. And so Sara Hivušić will tell us something about overview of projected climate changes over Croatia by the middle of the 21st century. So Sara is going to be on Zoom.
I'm very sorry I couldn't be with you today in person, so but thank you for the introduction. I will present you the expected climate changes in Croatia by the middle of the 21st century. These are based on the results of regional climate models. So, according to the latest IPCC report, the broader Mediterranean area is projected to experience persistent air temperature increases, along with an increase in the frequency and intensity of warm and wet extremes. These are accompanied by a decrease in the overall annual precipitation. These shifts in climate will likely result in a more frequent agronomic and ecological droughts, also in an increase in the occurrence of flash floods, especially in the northern Mediterranean. However, there is a high uncertainty regarding the changes in extreme precipitation amounts. So we aim to provide a more comprehensive insight into these expected climate changes and their spatial variability, particularly concerning the broader Croatia and Adriatic area. So in order to do that, we are going to assess mean annual and seasonal changes in temperature and precipitation and related extreme indices. And finally, our study aims to aid policymakers and stakeholders in formulating an effective adaptation strategies and mitigating the impacts of these projected changes. And this research work are done in the framework of the 8th National Report on Climate Change. So onto the methodology. So we are using regional climate models from the well-known Eurocordex ensemble at 0.11 spatial resolution. We have historical simulations for the present-day climate, which we are comparing with the scenario simulations for future climate. We chose the RCP 4.5 scenario. This is a moderate greenhouse gas concentration scenario, which you already heard. So our ensemble consists of 12 different simulations. Specifically, we have a combination of 3 regional climate models, which are driven by 4 CIMIC 5 global climate models. So we are using the DHIGMZ simulations done by RegCM 4.2, the Swedish RCR4, and CCLM4. And these models have been provided by the boundary and initial conditions from the same 4 global climate models. These are CM5, EC-Earth, MPI, and HUDGEM. So what we want to do is to estimate the climate change signal for future period, which this period represents the middle of the 21st century from 2041 to 2070. And we are calling it P1. We are comparing it to the historical period P0, defined from 1981 till 2010. We are analyzing ensemble means here and their annual and seasonal differences. We will present the differences in mean air temperature, minimum and maximum air temperature and precipitation, and also temperature indices of cold and cold and warm extremes, and wet and dry precipitation indices. So first, we are showing the results for mean, minimum, and maximum air temperature changes. So in the first row, we see annual changes, and the other rows show changes in winter, spring, summer, and autumn. It is obvious that on all of the maps, we will see a positive change, as it was expected. So there is a clear signal of an increase in all considered temperatures, and it's spread out across the entire country. For example, the mean annual temperature is expected to increase between 1.5 and 1.6, except over some mountainous areas, which show a slightly higher increase between 1.6 and 1.7 degrees. We see a similar increase for minimum annual temperature, with slightly lower increases over Slavonia. And projected increases in maximum annual temperature over the coastal mountainous area, Istria and Dalmatia, is between 1.6 and 1.7 degrees, and it's a degree lower over the rest of the country. If we look now at the seasonal changes, we see that the highest increase is expected during summer months for all considered temperatures, and this increase is between 1.8 and 2.4 degrees. And the mildest increase in air temperature is expected for the spring season, and it ranges between 1 and 1.3. So in most cases, the changes are slightly higher over coastal and mountainous area than over the lowland eastern parts of the country. So we move now onto the temperature indices, and we are starting with cold extremes. So we have here cold days, which are defined by absolute threshold as the number of days with minimum temperature lower than 0. Also, we have a few other indices. These are cold nights, cold days, and cold spell duration index. All of these are defined by percentile thresholds. So, and the changes are shown on annual and annual scale and during winter. We see that there is a general, general decrease in the number of days with cold temperature indices. So the map for the number of cold days shows the most pronounced decrease over central and eastern Croatia on annual scale and during winter. The highest annual decrease is more than 21 days, but mostly it's between 18 and 21 days. While in winter, we see a decrease around 11 to 12 days over central and eastern Croatia, and it's slightly lower over mountains. And the decrease in percentage of both cold nights and cold days on annual scale is somewhat higher across the narrow coastal area. And it's around 6% for both of these indices. Than over the central and eastern Croatia, where we see the changes are more spatially homogeneous than in the coastal parts. Also, we show a decrease of up to 5% for cold nights and up to 4% in the number of cold days. So the duration of cold spells, it decreases by 3 to 4 days in the most parts of the country, and it is slightly more over Istria and mountainous coastal areas. And in winter, the duration of cold spells is expected to decrease by approximately a day and a half. Moving on. On these slides, we presented the results for warm extremes, and we are showing changes on annual and on annual scale and during summer. So there is a positive change. We can see on all of the maps, and for example, if we look at the warm days, again, these are defined by absolute threshold. We see that we can expect to have at least 12 more days over Slavonia in future, between 15 and 18 over central Croatia, and even higher between 18 and 21, sorry, across mountains, Dalmatia and Istria, and the changes are even higher over the narrow coastal area. And also the summer contributes, of course, the most to this annual increase, from 5 to 17 days more approximately. For the rest of the indices, we can see a similar spatial pattern. So we have a minimum showing over the eastern regions, and then it gradually increases toward the central regions. And we see an abrupt increase over the mountainous regions. And it reaches a maximum over coastal areas. Only for the number of warm nights, we see some discrepancies over Gorski Kotar and Lika. So onto the precipitation climate change signal. So all of the further results here will be shown as relative changes in percentages. We see that the changes in annual precipitation amount are relatively small. There is an increasing signal over the Adriatic coast and across the country mainland, especially over the easternmost regions. But changes are negligible over most parts of Lika, Gorski Kotar area, and Dalmatia inland. If we look at the seasonal precipitation changes, there is an increase in winter, and it's most pronounced over the eastern regions. It's higher than 10%, while it's lower over the mountains and Dalmatia inland. The spring and autumn changes are very weak. Also, the summer precipitation amount will decrease. The largest decrease between 15 and 20% is seen over mountains, mountain littoral area, and central Dalmatia. And it's smallest over the northern most regions and eastern regions. If we now look at precipitation indices, we're starting with dry extremes. The annual number of consecutive dry days and dry days and consecutive dry days is projected to increase over the entire country, and the highest increase is over the mountainous regions and Dalmatia. The winter changes in dry days are almost negligible, while we see a decrease in the number of consecutive dry days over central regions. And in summer, we can expect an increase in both indices. And as expected, that is, the map showed similar spatial patterns as on the annual scale. So we look now at the wet extremes. So we see first the changes for the standard daily intensity index, then maximum one-day precipitation and 5-day precipitation. So on annual scale and during winter, we see that all indices show an increase. It is slightly larger over the eastern regions than for the rest of the country. However, in summer, well, we see a quite noisy spatial pattern. We see a possible decrease in intensity and maximum precipitation over mountains in coastal areas and Dalmatia, and central and eastern Croatia still show an increase in standard daily intensity index and maximum one-day precipitation. However, the maximum 5-day precipitation is a bit different over these parts. It is showing a decrease as in the rest of the country. And we have more wet extremes. So we show here the number of moderately wet days, and it is projected to decrease by the middle of the century. And during summer, we see a similar spatial pattern as an annual scale. This decrease is most pronounced over Istria, Dalmatia, and Lika and Gorski Kotar. So these changes are smaller over the eastern regions, and in winter, the changes are quite small, almost negligible. And if you look at the number of very wet days, we see a decrease in their number on annual scale, except over Slavonia, where there's almost no change. However, the amount of precipitation on these days will increase annually. So even though there will be less events when precipitation exceeds the 95th percentile, so we can conclude that the events which do happen will be more intense. And also this is in accordance with, with previous slide, where we show an increase in precipitation intensity on annual scale. During winter, the number of very wet days increases, and also the precipitation on these days also increases, meaning we can expect more frequent and probably more intense events during winter. While in summer, we have opposite situation. So some of the take-home messages. We see that the future temperature increase due to global warming will lead to a reduction in cold extremes over the entire country. Also, there will be an increase in warm extremes, especially in summer, of course, and across the mountains, coastal areas of Dalmatia and Istria. Also, we have seen that the changes in precipitation are much more complex to describe than the changes in temperature. We've seen that annual changes in precipitation, if we look at the moderate greenhouse gas concentration scenario, we see that precipitation amount changes will be relatively small, mostly because the winter and summer contributions to this change will cancel each other out. So during winter, we'll have more precipitation due to an increase in precipitation intensity, and also because the changes in precipitation frequency are minimal, and extreme events will become more frequent and intensify during winter. So this all implies that we will have an increasing risk of floods. Also, in summer, the fewer rainy days and extended periods without rainfall will lead to a reduction in summer precipitation and a decrease in extreme precipitation frequency and amount is also observed. So this all contributes to drought conditions, which are impacting water availability and agricultural activities during summer. So finally, as I have said in the beginning, this work was done for the 8th National Report of the Republic of Croatia under the United Nations Framework Convention on Climate Change. And if you are interested in a more comprehensive analysis, you can find the full version of this report on the DHMZ website under the publications. Or you can scan the QR code, but also there is a poster on this. So with this, I would like to thank you for your attention.
Thank you, Sark, for your very interesting talk. And we have maybe some time for questions. Okay, Branko.
How are treated Mediterranean and Adriatic Sea in regional climate models?
So I think most of the models in global that they take only the SST temperature. So from the global climate models. So the regional climate models are taking the SST, and I think that is it. So we don't have coupled simulations in this study.
So temporary SST is prescribed, basically. So
Yes,
there is no interaction.
Yes.
There is no.
No, there is no interaction. In
that's
future, yeah, that's a pity because we yeah. The Adriatic Sea is influencing the weather, of course, but in future study, I hope to look at the coupled simulations, but there's not much of these, so we will see what are the results.
Okay, thank you. One more question, maybe? No, so it's time to move to Slovenia to see what we can expect in Slovenia in the next century. So,
hello, thank you for announcing me. My name is Katja Klančar, and I come from Slovenian Environmental Agency. And I will speak about our project, the Climate Change Assessment in Slovenia until the end of the 21st century. The knowledge of past climate variability and estimation of future climate conditions are crucial for preparing expert bases for adaptation to climate change in Slovenia. And based on our long-term meteorological measurements and environment in the ARSO, we found out that in Slovenia the climate is changing faster than the global level. The project started in 2016, and we focused on climate change assessments for the future, their impact on extreme weather and hydrological events, such as heat waves, droughts, extreme precipitation events, frost, changing growth conditions and hydrological conditions on rivers, and other extreme weather events. For this purpose, we used the Common Climate Database from Eurocordex, and we used global climate models from the 5th generation and different representative concentration pathway scenarios. We decided to work with 3, and with the optimistic, the moderate, and the pessimistic scenarios. And due to the uncertainty of the models and the model results, we decided to analyze results of 6 combinations of global and regional models. That goes for the moderate and the pessimistic scenario. While for the optimistic scenario, fewer models were available, so we only did 2, which leads to some less reliable results. In selection process of these models, we chose those who best described the average climate conditions in Slovenia. And also we took into the consideration to choose different combinations of global and regional models. We did the bias adjustment for simulations, and it was done for the daily minimum and maximum air temperature at 2 meters for precipitation and for the reference potential evapotranspiration. For reference data, we used the national gridded homogenized observational data for the period of from 1981 to 2010. We used different methods basing on which variable we were doing the research on. And for precipitation, we used the non-parametric quantile mapping using the empirical quantiles with linear extrapolation. And for other variables, we use the quantile delta mapping method. The outputs are available in 12-kilometer spatial resolution on daily basis for the period of 1981 to the end of the 21st century. This was done for basic climate variables. To study the future climate, we divided the 21st century into 3 periods and we named them the near future, the mid-century, and the end of the century. The use of the ensemble climate models can lead to a wide range of climate change estimates, and the results do not always reveal at first glance if our conclusions can be drawn. And so we introduced a new indicator, which we named the reliability of change. This indicator estimates the coherence of climate ensemble and tells us whether the climate ensemble members show similar changes. First, we had to determine whether our changes are statistically significant. And for this, we used the Whitney-Wilcox test for each model and each model cell. Then we designed a so-called robustness test that has 3 levels. The no change, where less than half of the models have statistically significant change, and this is the green area. The high reliability of our changes, where half or more of the models show statistically significant change, and most of them show signs of changes in the same direction. And the low reliability, where half of the models or more show statistically significant change, but the changes are in different directions. We designed also 5 different graphical representations. Each of them is showing specific information and highlighting a certain aspect, whether that is spatial or temporal. Most of them are shown in the form of graphs or region average plots. Also very important for us was to show the reliability of change. And for this, we used the spread of model simulation results or a level of reliability resulting from the described robustness test. All of our graphic representations are available on our Atlas of Climate Change Projections, where you can simply choose from one of different representations. And then you go and you can have a drop-down menu, and you can choose whether you want to, for which climate scenario or a region or a projection in the future in terms of time. So now let's focus on the results. The air temperature in 21st century in Slovenia will continue to rise. Here on the figure, you can see how the temperature will change for 3 different scenarios. The thick line represents the median of all models, and the envelope shows the spread. We are anticipating that with the optimistic scenario, the temperature will rise for 1.3 degrees Celsius, with moderate model for 2 degrees Celsius, and with pessimistic for about 4.1 degrees Celsius. The uncertainty is increasing with time, so the further we go into the 21st century, the uncertainty increases. And the similar results are for all other seasons and across all regions for the temperature. And the temperature will rise the most in the winter, slightly less in the summer and autumn, and at least in spring. In contrast to temperature, the scenarios for precipitations are less reliable, as they're more diverse in time and space. Also, Slovenia's location is in part of the world where projected precipitation changes the direction of the signal direction. So in Northern Europe, the precipitation will increase, and in Southern Europe will decrease. As a result, our changes are less reliable. The annual precipitation will increase by 20%. In most of the country. In winter, this increase will go up to 40%, especially in the east. And in case of a pessimistic scenario, the numbers can go up to 60%. On the pictures, you can see the expected changes for precipitation for 2 emission scenarios on an annual basis. The left column of each scenario represents the relative change in precipitation compared to the reference period. And for 3 future projections, the blue shades indicate an increase and the brown shades indicate a decrease. The right column represents our reliability of change, where green means no change, orange means that the changes are reliable, and the gray means that the changes are unreliable. For the future, we're planning to improve our spatial resolution without scaling to 1 kilometer. And in a couple of months, we're hoping to update our project report with adding new variables from different fields, from meteorological, agrometeorological, and hydrological. Thank you for your attention.
Thank you, Katja, for your nice talk, and maybe some questions. Okay, madam.
I would like to ask you a question regarding our presentation. Do you see there any modification techniques, for example, for protection against flooding in Slovenia?
To be honest, I'm not quite sure right now, because I'm one of the newer members of the team for this project. And I'm not really sure if I can answer. Maybe one of my colleagues would be happy to answer.
Okay,
Okay.
let's to hear.
Anybody else?
Just a question on the temperature. You said that the temperature increase in the future will be higher in the winter than in the summer. But as far as I know, at least in Croatia, it's higher in the summer than in the winter. From already now.
The relative change, the changes compared to the deviations are going to be higher in the winter.
Okay. The variability will be increased. Okay.
Thank you.
Thank you very much. Okay, now we are moving from the regional scale to more local scale. And Kristina Šarović will talk about effect of climate change on water temperature and certification of Lake Kozjak.
Dobar dan svima, ja sam Kristina Šarović, student doktorskog studija koji malo predugo traje, ali sad se bliži kraju. Nadam se, zadnjih par godina se bavim modeliranjem temperature vode i modeliranjem vertikalnog temperaturnog profila u jezerima, pa bih vam danas prezentirala dio tog rada koji se fokusira, kako naslov kaže, na utjecaj klimatskih promjena na temperaturu i stratifikaciju u jezeru Kozjak, koje je nedavno rezultiralo i objavljenim radom u časopisu Environmental Science Processes. Kao uvod i kao motivaciju rekla bi par riječi o važnosti temperature i stratifikacije u jezerima, iako je to vjerojatno već intuitivno svima jasno da se radi o čimbenicima koji utječu na biodinamičke procese, utječu na transport nutrijenata i plinova, pa tako i direktno i indirektno utječu na biodiverzitet, kako na mikro i makrofloru i faunu u jezeru i oko njega. Kad je riječ konkretno o Plitvičkim jezerima, tu je jako bitno spomenuti proces koji je, ajmo reći, ključan za njihovo postojanje, a to je formiranje sedre i sedrenih barijera koji možete vidjeti tu na ovim lijepim slikicama. Dakle, radi se o procesu koji ovisi o kompleksnoj ravnoteži kemijskih, fizikalnih i bioloških parametara. Dakle, dešava se u određenom rasponu temperatura i kemijskog sastava vode, određene brzine strujanja, moraju biti prisutni određene alge i mahovina. Dakle, promjena temperature dovela bi do promjene svih ovih parametara koji bi utjecali na evoluciju tog jezerskog sustava. I sad ne želim zvučati pretjerano dramatično, no studije spominju, odnosno navode upravo taj proces stvaranja sedre kao glavni mehanizam nastajanja i nestajanja jezera u ovom sustavu kroz povijest. Naravno, pričamo o jako dugoj vremenskoj skali, no u geološkim pogledu to i nisu tako duge skale, tako da promjena temperature potencijalno može dovesti do morfoloških promjena u sustavu jezera. Evo, ako slučajno neko ne zna gdje su Plitvice, nalaze se u Hrvatskoj, u dinarskom krškom području. Dakle, tu koncentriramo se mi na jezero Kozjak, koje je 12. jezero u tom kaskadnom nizu, inače najveće jezero u sustavu i volumno i po površini. Za analizu utjecaja klimatskih promjena analizirali smo 3 RCP scenarija, dakle najekstremniji RCP 8,5 koji pretpostavlja da se ne poduzimaju nikakve mjere za smanjenje emisija, najoptimističniji 2,6 koji je i najnerealniji, rekla bi, i umjereni scenarij 4,5. Koristili smo podatke koje većinu kolega, što ste spomenuli, znači iz Cordex baze. Ovo su globalni i regionalni klimatski modeli iz kojih su izvučeni ti podaci, a ovo su godišnji srednjaci varijabli koji smo koristili kao ulazne parametre u našem modelu za simulaciju temperature vode. A to je bio model SIMO koji sam prezentirala prošle godine na izazovima, možda će se neko sjetiti. Radi se o pojednostavljenom modelu sa smanjenim brojem ulaznih parametara i cilj razvijanja ovog modela je bio pokazati da jedan takav pojednostavljeni model bez nekakve posebne kalibracije može dalje relativno dati zadovoljavajuće rezultate, što smo i uspjeli, pa je to bilo i objavljeno u časopisu Geoscientific Model Development. U ovom slučaju jesmo kasnije još malo doradili taj model i jesmo ga, pošto smo mogli, jesmo ga kalibrirali da što bolje opisujemo procese u jezeru Kozjak, tako da dobijemo što pouzdanije rezultate za potrebe ovog istraživanja. Za početak rezultati, tu su prikazane temperature i temperaturni gradijent u jezeru. Istraživali smo inače period do kraja stoljeća. Vidimo da u ovom umjerenom i ekstremnom scenariju imamo umjereni i malo jači porast temperature vode. I to vidimo da je taj porast temperature prisutan, dakle, ne samo u plićim slojevima, u epilimnijumu, već i u dubljim, sve do dna praktički jezera, što onda posljedično znači da ne vidimo nekakav jaki porast vertikalnog temperaturnog gradijenta, a isto tako ne vidimo da se ta termoklina, dakle dubina gdje je temperaturni gradijent najveći, dakle ta termoklina ne mijenja dubinu, a razlog tome je to što upravo znači to progrijavanje cijele dubine jezera, zato što praktički na jesen i zimi dolazi do konvektivnog miješanja kroz cijeli stupac vode. A još jedan razlog zašto to tu ne vidimo, znači ne kažem da nema povećanje jačanja stratifikacije, ali ovdje gledamo godišnje srednjake, pa se ti neki maksimumi koji se vide, gdje se vidi porast, tu se malo gube, a vidit ćemo ih u drugim rezultatima. Sada ovim bojama damo neke brojke. Dakle, porast temperature, srednje temperature uprosječene po dubini jezera u ova tri scenarija iznose, to su ove crne linije, znači 0,5, 1,4 i 4,5 stupnja u stoljeću. Brzina porasta u epilimnijumu, znači ovim crvenim, je nešto brža nego u hipolimnijumu, ali ipak temperatura hipolimnijuma, kao što sam rekla, relativno, ta razlika nije dramatična zato što temperatura dubljih slojeva prati temperaturu epilimnijuma. Ovo su i dalje znači bili godišnje prosječeni rezultati, no ako pogledamo šta se zapravo dešava po mjesecima, vidimo da posebno u ovom ekstremnom scenariju 8,5 taj temperaturni porast u površinskom sloju je puno izraženiji, što je i očekivano u ljetnim mjesecima, a dakle temperatura u kolovozu odnosno porast temperature je 6,6 stupnjeva u 100 godina i ovaj pik se zapravo poklapa sa pikom stope rasta kratkovalnog zračenja na površini jezera. Takve ekstremne pikove ne vidimo u ova druga dva scenarija zato što kod njih su stope rasta toplinskih tokova iz drugih procesa sličnog reda veličine, pa tu dolazi do među utjecaja. Generalno variabilnost temperature u dubljim slojevima je manja, pa tako je i ta stopa porasta kroz godinu relativno konstantna u sloju koji je pri dnu, a ovdje je to inače definiran, znači između 43 i 46 metara dubine. Što se tiče stabilnosti, odnosno stratifikacije, kao glavni parametar smo razgledali Schmidtov indeks stabilnosti koji je zapravo količina energije potrebna da bi se pomiješao vertikalni stupac vode bez izmjene topline prema vani. Iako se ne vidi zbog skale, u sva tri scenarija postoji signifikantni blagi porast srednje godišnje vrijednosti, a ove pune crte predstavljaju maksimalne vrijednosti tog indeksa i tu se već vidi, kako sam spomenula, da ti ekstremi, da pogotovo u scenariju 8,5 imamo znatni porast. Termoklinu, ako se sjećate u onom prvom dijagramu, dakle vidimo da ta prosječna godišnja vrijednost ne pokazuje signifikantni porast u niti jednom scenariju, no maksimalna dubina termokline u scenariju 8,5 raste za oko 7 metara po stoljeću, a u ovom umjerenom scenariju 4,5 neka 3 metra, ali ako uzmemo samo podatke do 2085. jer nakon toga dolazi do malog pada te dubine termokline. Zadnje što nas je zanimalo bilo je duljina trajanja tog perioda stratifikacije i meni malo iznenađujuće je bilo to što čak i u ovom najoptimističnijem scenariju početak stratifikacije je 5 dana ranije, a kraj, odnosno konvektivno miješanje oko 11 dana kasnije, tako da u 100 godina znači da bi trajanje stratificiranog perioda se produljio za čak 16 dana. U umjerenom scenariju to iznosi oko 28 dana i u ovom ekstremnom oko 47 dana dulje, što znači da ugrubo rečeno u ovom umjerenom scenariju stratifikacija traje mjesec dana, odnosno u ovom ekstremnom mjesec i po dana bi trajala duže do kraja stoljeća. Što bi rekla da je prilično ekstremno. Kao evo zaključak mogu samo ponoviti ove glavne zaključke, odnosno imamo značajan porast temperature u jezerima, odnosno u jezeru koji smo analizirali. Jačanje stratifikacije je umjereno, no njezino trajanje je znatno produljeno. I rekla bi da nije samo moderna fraza kad kažemo da su posljedice povećanja temperature brojne i imaju kompleksne povratne veze. Tako da što sve može se desiti zbog ovog povećanja temperature van okvira ovog istraživanja, no posljedice su ozbiljne.
Hvala Kristina na zanimljivim rezultatima. Da, očito se ne zagrijava samo atmosfera nego i jezera. Pa sada, je li ima kakvo pitanje možda?
Pitanje je, je li se možda zna koliko je vrijeme zadržavanja dubokih voda u jezeru? Je toplina dolje dolazi, je li, znači zračenjem, ali ako je izmjena elektrizna brza, onda će ona u nekom trenutku biti vezana i ići nazad na površinu, je li? Tako funkcionira stvar u stvarima, pogotovo što ovdje postoji također nekakav riječni dotok koji to sve skupa mijenja. Ako imate porast stratifikacije, tada će možda se smanjuje vrijeme izmjene dubokih vodenih masa, ne znam, ili možda imate kakav osjećaj za to?
Evo, ne znam napamet, možda profesorica zna bolje, ali koliko je vrijeme izmjene, ali inače baš jedan od pitanja je bilo da li možemo kod modeliranja jezera gledat ga kao posebno jezero, s obzirom baš da je to dio tog protočnog sustava, ali način na koji se tu strujanje odvija je tako da se uglavnom iz jezera u jezero se pretaču ovi površinski slojevi, tako da to miješanje je prilično, odnosno to stratificiranje miješanje je prilično izolirano. I imali smo mjerenja po vertikalnog profila, tako da model je bio evaluiran s obzirom na ta mjerenja i poklapanja su bila jako dobra.
Ako mogu samo dodati to, općenito varira od jezera do jezera, ali što se tiče Plitvičkih jezera, ona se u principu izmiješaju jednom godišnje u zimi i onda dođe do razmjene vode i još u iznimnim slučajevima kada se formiraju unutarnji stojni valovi, ako su oni dovoljno veliki, onda znaju se amplificirati, pa onda dođe do razmjene vode između epilimnija i hipolimnija. Ali u toplom dijelu godine, kad je jezero stratificirano, onda u principu nema miješanja, a voda koja teče iz jednog jezera u drugo je samo iz gornjeg sloja, iz epilimnija. A postoje jezera koja su cijele godine stratificirana, gdje uopće nema miješanja vode iz ta dva sloja.
Ok, hvala. Ja predlažem da sada krenemo dalje, da pazimo na vrijeme. Sljedeće predavanje će nam Romina Kraus reći nešto o planiranju monitoringa u luci Rijeka zbog očuvanja bioraznolikosti, gospodarstva i ljudskog zdravlja, projekt Protect Us.
Good morning. So when I received the kind of invitation to present project results, I realized that I will have to present the results of a project partner, Faculty of Civil Engineering. So don't expect much of technical details, but and the majority of my presentation will be about the motivation of this project. So it fits on the climate change and adaptation theme. Full name of the project was Development of System for Control and Protection of Ports from Introduction of Alien Species. So Protect Adriatic Sea, Protect Us. So why do we need to investigate and protect ports? The reason are ships' ballast waters. In order that a ship maintains its stability and maneuverability during sailing, in periods when there's insufficient cargo loaded on the ship, some ballast need to be taken into ships, and in the last century and a half, ballast water is used. This is actually seawater that is present in the port, and it contains all organisms that are present at that time in this region. The organisms survive the voyages, no matter how long and distant this voyage is, and they are released in port when this weight is no longer needed because cargo is loaded on the ship. These ballast water contains harmful organisms, and ballast waters are proven as a very efficient vector of organisms in these ballast water tanks. And these harmful organisms can be alien, invasive, toxic species, or human pathogens. So, of course, you presume that human pathogens can induce some illnesses for people, but these three type of species maybe you don't know by now. So toxic species are actually phytoplankton, also called harmful algal blooms because they induce these blooms. They are important for us because they produce compounds that are toxic for people when we use a shellfish for our food. Shellfish feed on filtering seawater, and if in seawater some toxic species are contained, they can induce some poisonings, which depending on the type of symptoms are called amnestic, diuretic, paralytic toxins, and in some cases these they can end in fatal consequences. So these are really unwanted and harmful organisms. The other two are alien and invasive species. So in species that are not native in one region can be transferred by ballast water from other region, and we call them alien, but there are several synonyms as non-native, non-indigenous, or okay, and if this non-native or alien species get acclimatized, they well develop in new environmental conditions, they can endanger local biodiversity and ecosystem functioning. And one of these, and then we call them invasive species because of these harmful effects. One of these is Mnemiopsis ledi, ctenophore, which was introduced by ballast waters in port of Venice, and from there it spread over the northern Adriatic, and it influences mostly fisheries, and particularly of small pelagic fish, because Mnemiopsis ledi is in competition with anchovy, as they both feed on zooplankton, and usually the Mnemiopsis ledi wins, so that the number of anchovy decreases. And in the Black Sea, there are very bad situation with anchovy, as and the fishery is almost completely destroyed, and hopefully this will not occur in the Adriatic as well. So through ballast waters, almost all kind of organisms can be transferred, because most of them have in their life cycle period when they are larvae or eggs, and these as a microscopic dimension, they can easily be transferred by ballast waters, and they actually are. And with climate changes, it is considered that the likelihood of the successful adaptation in new areas will increase, and that is expected to occur also for human pathogens, toxic species, and other alien species as well. This problem was recognized by International Maritime Organization with the International Convention for the Control and Management of Ships, Ballast Water and Sediments in 2004, which was about a century after the first negative consequences of ballast waters were determined. So, and the convention, the basic provision of convention are that without delay or jeopardizing the safety of the ship, it should be avoided to take or discharge ballast water that potentially contain harmful organisms. This should be done through port monitoring and early warning system, and alternative locations for loading ballast water should be designated when there are harmful organisms in the port. This should be during convention also defines that each ship has to have a ballast water management plan developed, and they should install ballast water treatment system, which should enable most of the organisms to be destroyed in the ballast water. And these were the objectives of Protect Us project, port monitoring and early warning system development. So the ballast water after this treatment should contain less than specific amount of organisms of a specific dimension or of pathogens, specifically Vibrio cholerae, or indicators of other human pathogens in the sea water. So, and IMO tests and approves these systems that and approves their installment on ships. So we didn't, of course, start from scratch, but there were some questions that we wanted to further investigate and to complete a port monitoring protocol with the questions what do we need to monitor, at where, which positions, at what frequencies, and how, so with the use of specific methodologies. Of course, I cannot now present all our results, so I will focus on question where. We actually continued to investigate stations that were investigated in the previous project, and we did investigation in Northern Adriatic port of Rijeka and Southern Ploče. In each of these ports, there were two stations that were directly influenced by ballast water and one indirectly. I will show only results for Port of Rijeka. So numerical modeling of our colleagues. They did for the Port of Rijeka, so we can understand better what is the circulation in the port, which could help us determine some of the issues regarding the spread of organisms. Firstly, the results of the modeling of currents were used. So here are meteorological data. So in this work, information about wind conditions, which primarily drives circulation in the port of Rijeka, were used. So frequency, intensity of winds, which influence circulation, and the obtained results were used to define alternative locations for ballast water intake in cases when harmful organisms would be in the port, which and these locations are outside the port, but the spreading of organisms from the port, to better understand it, we needed these circulation patterns, which were done in for all seasons during the year, according to wind regimes. And further modeling was done. Sorry for this. Were done to investigate how a specific type of cells are can spread over the port, and after several time periods of 1 hour, which you unfortunately cannot see, 6 hours after half day or entire day, where they actually sink or spread in the port. And these results were used for determination of additional stations in the port where sediment should be monitored to check if there are some cells or organisms have accumulated on the sea bottom. And specifically this was important because there's a group of toxic species which can during their life cycle develop a resisting stage where they sink at the sea bottom, and due to bad environmental conditions for their processes, and when again positive environmental conditions are present in the seawater, they rise up in the water column and again they reproduce. So for this purposes, 2 additional stations were chosen in the Port of Rijeka to include them in port monitoring beside the previous mentioned stations. So in conclusion, climate change will increase the likelihood of successful adaptation of introduced organisms by ballast water, no matter then, despite the fact that ballast water will be treated, they can still carry some cells that can reproduce in the receptive port. Their harmfulness manifests in ecosystem disturbance, as showed for Nemiopsis ledi, and they can have impacts of human health, such as toxic species on economy, tourism, fisheries, and mariculture. And for this reason, it is necessary to establish and implement port monitoring, after which we can raise awareness of an alarm population in the region not to take shellfish for food or exposed to sea. Which is especially important in the summer, and also to try to contain the spread of these alien and invasive species by some methods that can be applied. So in the project, beside colleagues from civil engineering. There were also colleagues from a Public Health Institute and from a Maritime Studies University of Rijeka. And our lead partner was University of Dubrovnik. Thank you.
Thank you, Romina, for your nice talk and nice work. We sure don't want aliens in our sea. So some questions maybe? Sorry.
I have an idea. What do you think? Would it be possible to treat tank and ships with ballast water with some, let's say, chemicals or something to kill everything which is harmful, with chemicals which is not harmful for the sea when the ballast water is out?
Yes, these are these systems that will be installed on ships as part of ballast water management plan, and they should be installed on all ships all over the world in the countries that ratified the convention in less than a year. So there are different methods, chemical, UV treatment that suppress the number of cells. However, there's no method that kills all organisms, and even a few cells are enough if the environmental conditions are good for these species, they develop. So it will be less negative consequences, but not completely threat cannot be removed. But you, of course, yeah.
Thank you. We have, I think, 2 more questions, but quickly.
Ja sam Nirvana Franković iz Fonda za zaštitu okoliša i energetsku učinkovitost. Ja bi nažalost imala jednu primjedbu. Fond za zaštitu okoliša je osigurao nacionalnu komponentu 15%, to ste propustili predstaviti u početku, a imali ste i ugovornu obavezu simbol fonda staviti na sve oznake. Pa evo, ja koja sam osobno radila s kolegama na tome zadnje 3 godine, stvarno smo imali velikih problema u provedbi i osiguravati ta sredstva, pa evo malo sam se osjetila. Niste ispoštivali ugovornu obavezu. Hvala.
Pa srećom, pa je projekt gotov. To je jedino što mogu reći. A baš sam se trudila, dolje na svakom slajdu su, ali evo, znači promakao mi je. Ja se ispričavam. I da, zaboravila sam, odnosno nisam stavila da smo imali 100% financiranje zbog dodatnih 15% od fonda.
Ja vjerujem da ta nacionalna sredstva su nam svima bila jako važna, tako da ja u svakom slučaju pozdravljam fond koji je pridonio i drugim projektima, ne samo vašem, a ovo je propust. Ja se nadam da ćete ispraviti pa ćete dodati ovoga u svakom slučaju u sljedećem predavanju, ali fondu svakako ide zahvala, ja bih rekla, od svih nas koji smo koristili ta sredstva. Mislim da Daniel ima jedno pitanje.
Yeah, I just one ignorant question, but I'm wondering, so in your schematic with its vector story, so a ship takes some ballast water somewhere very far away and then brings it here, right?
Yes.
But is it technically possible to make it kind of gradually release some water and take it as it goes, so that it kind of dilutes, let's say,
yes,
over time, and then doesn't make such a huge step change in these species?
You are also right. This is method that is used right now. For the time being. So the ballast water was expected to be exchanged on the way of the voyage, which can be applied on long voyages, but not on a short span, like across the Adriatic. So there's not sufficient time or designated locations of depth and distance from the coast to do the exchange. And yes, the idea was that on the open sea, the salinity is different, so the organisms cannot survive. But it was found that the results are not satisfactory in decreasing the number of organisms, and this method is going to be replaced with the systems that will need to be installed in a year's time.
Okay, thank you very much again. And now it's time for the next presentation, which is agriculture risk metrics. And it will be given by Christopher Žegnjar. Okay, thank you.
Dobro jutro. Am I audible enough? Right. Very pleased to be here. I believe I'm one of the only non-scientists, and in the scientific community, it's wonderful for us to dive in. The last 2 days, this very detailed scientific work that you've been doing is fascinating, and you'll see why. I'm going to show you a platform, a web platform. So I'm going to take you up to 30,000 feet, and all of what you're doing is there on the ground, the ocean. Agriculture risk metrics, that's 3 words. We are a consulting and analytical company based in Munich. I've spent since 2019 a lot of time in Croatia. We've been studying agriculture. We've been working with some of you, with DHMZ. My partners in this initiative are sitting here, Mario Njavro, Zagreb Agriculture Faculty. And then where we come from is economics, first of all. So everything we've talked about is a risk, is a scenario, but how much does it cost, that scenario, if it's true, in 5 years, in 10 years, in 25 years? We know what's happened in the last 20 years because we have the data. So basically, you can see climate change creeping in. That's why it was so interesting. A lot of your work is there in numbers, based on trends that we see in the last 10 years in Croatia. Drought. So metrics, of course, is figures, is numbers, is statistics, is data, and is modeling. Good metrics and a bad model is not a good combination, and vice versa is not a good combination either. So we're always looking for best practice data. Then we have to talk to you. You know where the data is. I don't know where the data is. Mario knows where the data is. So Mario has helped us find the data we need in Croatia. And then modeling is surprising how much there is, right? Yesterday you saw Stefan Niemeyer, his talk, JRC, European Union. We pay for him, by the way, right? We're taxpayers. That's our money that goes into the huge research center that Stefan Niemeyer, Mars, food security, and then next year, what is the probability that what we've produced in this year is going to decrease or increase next year? And then, of course, we've got global trades. Food comes from everywhere today. So these are the things we're looking at, the economics basically behind climate change. Climate change is the very big focus. So what I'm going to run you through, first of all, the impact of climate change on crop yields in Croatia. Yield is money. Yield is basically all the crops, right? Their production, what they fetched in the marketplace. Not just climate relevant, of course, prices can go up and down as well. Then just a few words, because I think I've got 3 minutes before the coffee break, so I have to be quick. Predictive analytics, forecasting, risk modeling, early warning. We advise the insurance industry. They have to know pretty precisely the monetary side of things because they pay for the losses if they insure them. So, and then just the importance of high quality, up-to-date agro-meteorological data. That's the core of the conference. So basically, you should know that the more and the more often and the better the data, the more precisely we can, the more precise we can be on monitorizing the drought in Continentalna, or the border damage on the coast in the vineyards. Then we've created a web platform. So we started actually as a European Union funded project. That's how Mario, we got to know each other. And that's wonderful that there is, let's say, this work going on. Agriculture is fiercely national. It tends to be very national. So it's all very good to look on the neighbor's garden and understand and learn things that they're doing. And if they're good, bring that back into your own country. And then the actual web service platform, if you like, is an ecosystem because we're linking up here all the stakeholders in agriculture. Public sector in Croatia is very difficult to get contact with. Science, quite easy. And we've been working in projects together. So what have we seeing? The increase in extreme temperatures, we saw all of this in work that's going on. is impacting quite strongly. And we have data from the damage register of the Ministry of Finance, and that shows that the biggest economic losses come from 3 climate-related perils: drought, flood, and frost. Drought we introduced, we did the analytics for the insurance that there is in Croatia. Croatia Osiguranje started insuring drought last year. So the effects of climate change, changes in product quality, decreasing yields, higher costs, and all of that leads to fluctuating incomes for the farmers, who run to the ministry and complain that not more is being done to protect them. So I think the big question that we ask ourselves, how can we provide better forecasting frequency? How often? And IPCC, the climate work that some of you are doing, that's clear enough. The frequency is increasing. How precise? Is that convective storm of July this year going to be a 1 in 4 or 1 in 10? A few years ago, it was a 1 in 25, 1 in 100. And now what we're reading from IPCC, and I'm talking about the Balkan countries, Italy, Spain, Greece, we're seeing this is probably, we would say, 1 in 3.5. It's nothing scientific, it's just what we're seeing in trends emerging, that kind of convective storm. So what we're setting out to do with the platform is to lay the ground for better forecasting generally. Then this is a live dynamic platform. The more data and the more analytical work that we upload into it, the more precise the output becomes. So you have to imagine the output is like Google. You want to know about these 2 ladies have a vineyard in Dalmatia, right? And then what I can do is we can visit the vineyard, geocoded. We can look at the last 20 years of risk profile, but we can also, with Cordex data, project the next 5, 10 years. So that's what we're doing. Probable, but possible. For an insurance company, of course, has to be looked at as well. It's nice having the probability, but the possibility could be your ruin if it exceeds the probable by a big amount. Then our approach, if you like. So what we're looking to do is combine the skills and know-how of science and the insurance industry to achieve more awareness of the threats and a better preparedness. And we look to develop and operate, first of all, a holistic approach, everything that impacts, every single risk there is for agriculture. We look to get, with your help, Mario, in our case, best practice data sources, clean, digital data. If it's not digital, we can make it digital. We have heavy technology behind the platform. Agree data standards, best practice risk models. That's very difficult. There are many of them, but then if we ask the community, what have you seen that is better than what there is before? And then you get an opinion. The data mining structuring algorithms is what makes this platform dynamic. Once we've found a data source, we stay on the data source. When there's a new set of data, we upload that set of data. So it's not just a one-off platform with history, it's a dynamic platform. So interesting too, you know, this was all destined for the insurance industry, but where we've worked with scientists, the scientists have really fallen in love with the platform. To have all the data in one place, you can do completely different analytics and R&D work than if you have to go out and get data from here, data from there, and data from there. And then to scale this all up, to provide better, that's what we're talking about. What's early warning, right? In flood, JRC in Ispra gives a sort of a 5-day warning of a weather scenario that can lead to heavy flooding. So basically, 5 days to prepare is not much, but I mean, it's better than 1 day or no days, right? So when we say, and I saw some of the presentations, there are some pretty clear statements on agriculture in 5 years and 10 years. So it's validating that. And then mitigation adaptation as a function of what you see. And you scientists have a very clear view. And if you read the IPCC publications, 1,790 scientists, it's a very clear view, right? So mitigation, adaptation is what we're talking about. There's no sudden remedy. We're going to have this frequency, we're going to have this severity, and we better prepare for it. So we are in touch with scientists quite a lot, and this is really the predicament that they face, most of them. This actually is a graph from Wageningen. Collaborative infrastructure, like you are here today in this. I like the faculties, right? The different faculties who came together here to organize this. Geoscience, meteorology, agrometeorology, and mathematics, statistics. So collaborative infrastructure, data management is not a strong point of many of the scientific institutions that I know. So that's something to think about. If I look at a big insurance company, it's about 20 years now that they've been using data mining, data structuring, automation of data, bringing data together for motor insurance, for life insurance, not really for crop insurance. Crop insurance is not a very big line of business. So basically that is yet to be done. Analytical tools, if you have all the good data in place, you can automate certain things that you want to see. And I'll show you that in a minute. So the outcome of this study survey by Wageningen, there's a strong need for a lean ecosystem enabling digital climate risk research in agriculture, data governance, multi and transdisciplinary research, jointly develop data science solutions, accuracy, and then all of it is about speeding up the research into the impact. And then we're back to Mario and the money, the economic impact for a country, for a sector, for agriculture. So that's the reason behind, and that was quite a long run in us building this platform. We've used now already most of the public data that we've been able to find and have uploaded this. You can see your lovely country. It's an incredible shape. I don't know any other country that has a shape like that. The boomerang, and then agriculture's in the middle part, Continentalna mainly, right? That's your big sort of grain production, the sugar beet. The coast has vineyards and it's like two countries in one country. You can show that statistically and historically. The damage, the drought is where the big field crops are in Continentalna. It doesn't affect the coast in the same way. And we've seen, different rainfall. So we set this up originally under R&D, under a project funded by Eurostars. That's a part of the European Union's funding. And then the idea was to give consideration, and this is where the agroeconomics faculty of Zagreb comes in, the needs of the farmers, the needs of agribusiness. The needs of researchers has been added on because the agroeconomists are also researchers. So basically they've had access to this data. And Tajana Chop, who's sitting here in the room, has done drought research using the platform and has published a PhD paper. So it's all about, how to serve the stakeholders in agriculture, better data, better analytics, and a monetary situation going forward, a damage situation, realistic disaster scenarios. What you see here in the graphs, there are dashboards. We can look at any part of the country, we can look at any crop, and we can show the impact of the last 20 years of fluctuating results. We correlate with meteo data, and then we use all of that for trends moving forward of the impact of climate change. And this is where, of course, your modeling comes in. You're closer to it. You will understand it better. So you can see there's the country broken down into the regions. You can see the different impact of the perils in the colors there per region. So we use big data, we use the latest scientific insights, and we combine all of this into one platform. And the idea being, when the insurance company talks to the farmer, they can actually go in here. Zagreb agriculture faculty have done tests with the bigger farmers, and the bigger farmers like this. They can determine their own risk profile on their farm and the impact of climate change going forward. So there are many people who can work together on this platform. So we have the granularity of the data we have. And of course, we'd love to have it even more granular. We can break it right down into region and crop, as I said. Smart and customized analysis through the automation of these dashboards. You can generate whatever the menu, whatever you want to see, you can upload and generate it. We update the data every time there is an update in the original database. And on the right side, we're missing the public sector. We have talked to the ministry several times. They like the idea. There's a tool that's being developed called Savjetnik for the farmers. We think this would be a perfect fit in there. And for one reason or another, this has not moved forward. So one risk view, not many risk views. There's one risk view. If all the scientists of Croatia and of the world come together and analyze, I think it's a pretty strong view. But then is this getting out there, right? So a lot of people have short-term view, right? And that's what it looks like. That's the dashboards you can see on the right. Calculating frequency and severity of climate risks, individual risk profiles on a county level, mitigation, adaptation, then mapping of natural perils, including drought. That's some of the work of Zagreb Agriculture faculty, which is partly done using the web platform. And a great thank you to them. They've sort of taken me inside Croatian farming. Otherwise, out of Munich, all I can do is use my telescope and look from a distance. And then I've looked bottom up at farming in Croatia. We know how many organic farmers there are. We can go and look at organic farming if we want. We can look at any aspect of Croatian farming with the know-how of those people who are studying it every day of their working life as scientists. So to sum this up, it was a great support we got from Zagreb Agriculture faculty. We, of course, want to co-design and with the Croatian institutions, how this moves forward. It's live, this platform, it's there, it can be used. What we're always keen on doing is finding new data sources that can be uploaded and put together. And then, as I say, in the private sector, Croatia Osiguranje use this platform. They use this for their own risk assessment when they insure farms, and they used it also to introduce the drought insurance, which was introduced in 2022. Then I see that we see the platform too. There's the Green Deal initiative. Your ministry has filed a 1,300-page document to Brussels, stating the plans for the Green Deal that Croatia is going to implement, and then that, interestingly, can be monitored, right, here through a platform like this. And then, as I say, where we've worked with scientists, we're doing the same in Italy at the moment. They are the first to want to use the platform, above all the agricultural economists. That's really the conclusion. We invite you to reach out to us and discover. If you want to come and visit the platform, have a look at it. You can do so anytime. We can give you access. We're interested to learn about your needs for analytics. And what we would like is, of course, your help to create this as an ecosystem, so that all people who would need this actually get it. And then, therefore, a license is needed. So, and then, again, I close with the word, let's all work together to speed up the research into the impact of climate change. Thank you. Hvala.
Thank you very much. Well, we're running with time, so I suggest that any questions can be discussed during the coffee break, because we have 15 minutes or a little bit more for coffee.
And it's
Okay.
it's my fault.
Okay. Okay, thank you very much.